And if you have any questions, you can type those questions and then I'll stop and I'll read them and answer them. Okay. So today I'm going over 2.6, which is combinations of functions. This is relevant to your assignment. There is, I forget which question 6, I believe, where you're doing combinations of functions. So what we'll do today will help you on those questions. So 2.6 covers adding, subtracting, multiplying, and dividing functions, and also finding the composition of a function with another function, which is basically where you plug one function into another. And then using combinations and compositions to model and solve real-life problems. So I'm actually going to go through everything here. So I'm going to go through the adding, subtracting, multiplying, dividing, the composition. I'm going to show a real-life problem on why you would be doing composition of functions. And then I'm also going to connect it back to function transformations. So combinations of functions. These are referring to adding, subtracting, multiplying, and dividing functions. And the important thing is understanding the notation and what it means, because the biggest thing I see are people getting the notation confused and then they do the wrong thing. So you really need to pay attention to the notation so that you know what it means. So if we are adding two functions together, we will write it like parenthesis f plus g of x. Sometimes it will just say f plus g and it won't have the x thing. So sometimes you'll see it just like f plus g, like that. That still means you are adding functions. And so that is literally taking your two different equations or your functions and adding them together. The difference is very similar, but that is just written with a subtraction instead. That just is written as f minus g. If you see fg, that is multiplication. So that is f times g. And you want to be very careful, because if it's written with a closed dot, that's multiplication. If it's written with an open circle, an open dot, that means something different. So just because there's a dot in between the f and the g does not mean it's necessarily multiplication. You need to pay attention to whether it's a closed or open dot, essentially. So if it's a closed dot, or there's no dot at all, it just says fg, that's multiplying your two functions together. And then if it's one's written over the other one, f over g, like a fraction, that means you are dividing the functions or writing them as a fraction. So we're just taking different equations and combining them in different ways. So the assignment, actually, there's a question about the quotient where you're dividing them. You're writing one over the other. So I'm going to basically use the same f and g for all of my examples here to show what they look like, all these different things. So we've got f plus g of x. So that means, you can kind of think about it like you're distributing the x. So that's f of x plus g of x, if you want to think of it that way. So we're literally adding the equations together and then simplifying if possible. So f of x is x plus 3. Oops. And g of x is the square root of 1 minus x. So we're adding those together and then we're simplifying if we can. Now in this case we can't simplify because we don't have any like terms. If something's underneath the square root, you can only add it to things that match underneath that square root. So that's as simplified as that goes. So that is your answer. You're just adding those equations together, and I can highlight the x plus 3, that is your f of x. And then if I switch to a different color, your square root of 1 minus x, that is the other function. So you're just literally adding those together and then combining them if you can. F minus g of x, that is the same thing, you're just subtracting. So if f of x minus g of x, which gives us x plus 3 minus the square root of 1 minus x. And again, that can't be simplified. Now, if you're subtracting and you have something with multiple terms, it's always best to put parentheses around it, because when you're subtracting, you do need to distribute that negative sign. So if g of x, if instead, let me do this in a different color. If we had instead g minus f of x, we would have the g of x first, and then we'd be subtracting f of x. And since f of x is multiple terms, we'd have to have parentheses there because we would need to distribute your subtraction sign. So you want to be careful when you're subtracting so that you pay attention to whether you need to have that the parentheses or not. So I'll just box that. Okay, same f and g. Now we're going to look at the multiplication and the division. So f g of x, that is f of x times, so closed circle, g of x. So f of x is x plus 3. G of x is the square root of 1 minus x. So you can keep it that way. That's completely fine because it's a square root, but oftentimes you'll be combining it with something else where you can actually FOIL and you can distribute. So if we wanted to, I could distribute and write that as x times 1 minus x plus 3 times 1 minus x. So if you can simplify it, do so. Because multiplying it out didn't give me anything that I can simplify, I don't really have to do that, but sometimes it does. So you'll need to check that and see, okay, if I multiply this and I actually do FOIL or whatever I need to do, is this going to actually give me things with like terms that I can add? And then we've got f over g of x, so that is f of x over g of x. So you're creating a fraction. So f of x is x plus 3, and g of x is the square root of 1 minus x. So generally, we just leave it like that. We don't really rationalize the denominator unless it's only numbers. Because our denominator has variables in it, we don't really worry about having that square root in the denominator. We can leave it like that. It saves you some work. So it's really just, you're just writing one function over the other. Sometimes you can simplify it and actually like reduce things, cancel out common factors. Sometimes you can't. So adding, subtracting, multiplying, dividing is just literally doing what it says and then simplifying it if possible. So the homework assignment has a problem like this division, and it has a square root, and so really it's just a practice in, do you know what the notation means? That's what the goal of that question is on the assignment, is do you understand the notation and what it means? So that's, you know, what we're looking for there. So are there any questions on example 1 or example 2? Okay. Now, the next thing is composition of functions, and this is the hard part for a lot of people, because this is where you are plugging one function into another. And so this is where I said you need to pay attention to the circle, because it's an open circle. So it's not an O, it's not a 0, it's an open circle. So when I write that, that's how I write it. So oftentimes you'll see it written like that without the X. It looks like it says fog. It doesn't. It's an open circle. It's function composition. It means that you take the second function that is written there. So if you see f compose G, that's how we read it out loud, F compose G, you're taking the G and you're plugging it into F. So it's going inside f of x. And so that makes the domain stuff tricky, but we're not going to worry so much about domain and figuring out the domain and what that means. You're not going to be really tested on that. What's important is being able to actually do the function composition, where you're plugging one function into another. So this is best seen with demonstration. And again, I am going to color code because this will make things a little bit easier. So I'm going to keep f of x as yellow, and then g of x as green. So f compose g. This means I have f of x and I'm replacing it with g of x. So g of x is getting replaced in f of x. So everywhere, instead of f of x, everywhere I would see x, I am now replacing it with g of x. So my f of x is equal to x plus 3. So that means instead of x plus 3, I would have g of x plus 3. So I'm hoping that the color coding here, you can see that compared to f of x, x is green, equals x plus 3. So f of g of x equals g of x plus 3. And then you replace g of x with what the actual expression is, or what the equation is. So that is the square root of 1 minus x plus 3. Which in this case almost looks like we're adding them together, but not quite. So it's not exactly the same as f of x plus g of x, but it looks sort of similar. We're replacing the x with the other function. Now the other direction, g of f of x, so this is g where you're plugging in f of x. So going back to my highlighter, instead of x, I'm replacing it with f of x. So when I write this, g is the square root of 1 minus x, but instead of x, I'm replacing it with f of x. So I'm plugging f of x in for x. So then I need to replace f of x with what it's equal to, which is x plus 3. And I'm putting parentheses around the x plus 3 because I'm subtracting it and there's multiple terms. So now I need to simplify in there, so I'm going to distribute that negative. So that's 1 minus x minus 3. And then I combine like terms. 1 minus 3 is negative 2. So it's negative 2 minus x. And then that is the simplified version where we plugged in f of x into g. So we replaced g with f of x. And so f of x, again, that is x plus 3. So if I'm trying to color code here, everything g is green, everything f is yellow. So you're replacing it inside another function. And so there is a question similar to this. The question, it's like part B on number 6 on the assessment, or the assignment. And so you're replacing one function with another, and then you need to simplify it. Are there any questions? Okay. So now I'm going to take a look at why is this important? How is this used in the real world, basically? Why would this be something that you would ever want to do? And so this is a word problem from the text. I forget which where I found it. It might have been in the problem solving at the end of chapter 2. But I think this is an excellent demonstration of the function composition and what it means. So your company orders a load of rock salt at a price of $85 per ton. There's a delivery charge of $95 and sales tax is 7%. So this example is great because we're also explaining what everything means. So it's not just, okay, we have these equations, is what does this mean? So we've got A, B, C, and D. So let's look at part A. Explain what the function d of x equals 85x plus 95 represents. So 85 times x, if it's $85 per ton and we're multiplying it by x, that means x is the number of tons. So I'm going to just write that down. Number of tons of the rock salt. And so 85 times x tells us the price of the rock salt. So 85x is the price of the rock salt. $95 is the delivery charge. And so our function d of x is basically taking the price of the rock salt plus the delivery charge. So it's giving us the total charge after delivery. Is the cost after delivery. Because it's the cost of the rock salt plus the delivery charge. So it's basically the total cost, if you want to think of it that way. So this is the process. If you're interpreting or you need to explain what a function means or what the numbers represent, which is a skill that you need to do for this week's discussion, is you write an equation, but you need to also tell us what the numbers represent. This is how you do it. You explain, what does your input mean? Okay, you're multiplying by that input by a number. What does that mean in real life? Okay, you're adding something. What is that in real life? So you're putting all that together. What is your actual function telling you? It's giving us the total cost. So that's part A. Part B says write a function c of x for the total cost of an amount of x dollars with 7% added. So I'm going to squeeze this in. So we're writing c of x. In this case, x is not the tons of rock salt. It's telling us x is the amount of dollars. So our input is something else, but we're using the same variable. That is fine, as long as you know what the variable means. So our input is the amount of dollars, so the total cost. So if you were adding tax, you're basically taking whatever your cost is and multiplying it by 1 plus the amount of tax. So if our tax is 7%, as a decimal that's 0.07, and so to find the total after tax, you're multiplying whatever your total is by 1.07. That's how we figure out the total after tax. It's 1 basically for the amount plus the 0.07 to get the total. So our function for the total cost with 7% tax added would be 1.07x. So now we've done A and B. Are there questions before I go to C and D? Okay. So I was smart and made a second slide for C and D because I knew that I would run out of room. So C, find and interpret D compose C of x and C compose D of x. So we're looking at the function composition and what that means. So let's start with D compose C. So that means you're taking D and you're plugging in C of x. So that means we have 85 times c of x plus 95, because instead of 85x, I'm replacing that with c of x. Now c of x is 1.07x, and then we have our plus 95. And so now I need to multiply my 85 times 1.07. So I'm grabbing a calculator. And that gives us 90.95x plus 95. So it says find and interpret. So if we look at this, c of x is basically the total after tax. It's basically, it tells us how to calculate tax. So when we plugged it in this way, the part with tax is only added to the $85, the price per ton. And in this case, our input, x, is still going to be the number of tons because that's what x is for D. So we've got $85 per ton times 1.07, so that's taxing the dollars per ton, times the number of tons. And then we've got plus 95. So this would be the total cost plus tax if the delivery charge is not taxed. If the sales tax is only on the rock salt and not the delivery, because we're not multiplying the $95 by tax. So interpret means this would be the cost if only the rock salt is taxed. Because that's the only part of the equation we multiplied by 1.07, the equation for tax. Now going the other direction, C compose D, so that is taking the equation for tax, C, and you're replacing it with D. So our equation for tax is 1.07x, so that's 1.07 times D of x now. So that is 1.07 times 85x plus 95. So you multiply that out, you get 90.95x plus 1.07 times 95, 101.65. So the difference here, we're still taxing the $85 for the rock salt, $85 per ton, but we are also taxing the delivery charge. So this is the cost if the delivery fee is also taxed. So you can see that there is a difference in the function composition based off of which one you use, which one you plug into the other. They give you both useful equations, but they mean different things. So, and this is one way that you can use a function composition, is if you know there's a specific way things are taxed, you can write a function for that, and then you can write a function for how to calculate the total based off of various things, and you can plug one into the other. You just have to make sure you do it in such a way that you're taxing the correct things. So now part D says there is no tax on the delivery fee. Find the company's total cost for 13 tons of salt. So unfortunately, I ran out of room here and I didn't create a third slide. But if there's no tax on delivery, that means we're doing decompose C. Yep, decompose C, and we're plugging in 13 for X. So you could write it as decompose C of 13. And now I'm sort of, why is it not letting me write? There we go. And now I'm going to plug 13 into the equation, and I'm going to just not show the work, but I'm 13 in for x, so it's 90.95 times 13, then plus 95. And that gives us 1277.35. Squeezing that in there. So this is a real useful way to write equations, especially let's say you work for a company and you know that tax is calculated the same, but the cost of things are different. You know, let's say you have rock salt, but then you also have people doing gravel or doing other types of things, and so the prices are different, and maybe the delivery charges are different. So you can write equations for each of those separate types of items, and then have a single equation for tax that you can use to calculate it out. And this is something that's useful in Excel because you can create these in Excel and then let Excel do the math for you. Because Excel basically is a way that works with functions. So a lot of people when they're doing Excel, they don't realize they're actually doing algebra. So this is a really neat thing. You may not say, okay, what I'm actually doing is function composition. So that's why I like this example, because it really shows you what this stuff means. Okay, and now let's connect this to transformations. So sections 2.4 is about like different types of, let's see, 2.3 was graphs of functions or like family of functions, and then we had function transformations, I think was 2.5. So we're going to connect this to function transformations because some of the function transformations you're doing are basically combinations of functions. So let's say you're doing a shift left or right. You're taking a function where you're adding something to x, because shifting left or right means you're adding and subtracting to the x value. So your g of x would be x plus or minus some value. You're plugging that into another equation. That is a function composition. A shift up and down is a function addition or subtraction, where that g of x you're adding is a number. And then when we do function multiplication, that's a stretch or a shrink. You're multiplying your function by a number. So this will make more sense if I actually do an example here. So for each transformation, determine what f of x is, what g of x is, and the function combination that happened. So f of x, that is what we're going to call the parent function. And then g of x is going to be the transformation that occurred to that, or the directions on how to transform it. So I've got h, j, and k of x here. So h of x is x squared minus 2. So the basic function we're looking at is an x squared function. So our parent function, f of x, is x squared. Now, if I go back to h of x, I subtracted 2 from that. So g of x would be my function, say x, minus 2. And what we did is we plugged x squared in for x. So we are plugging f of x into g of x. So that gave us, instead of x minus 2, gave us x squared minus 2. Or, because it's just a constant, we can think of this as we simply, if we have g of x as like a constant, I should do this in 2 different colors. Hold on. I'm going to try to, because there's multiple ways you can think of this. So you can think of this as a composition where we plugged x squared into g of x. Or, if I switch colors, if we say g of x is just going to be negative 2, then this is f of x plus g of x, which gives us x squared minus 2. So you can think of that in 2 different ways. You can think of it that we plugged in something, we did a function composition, or we did a function addition. And if you think of it as the function addition, then we are shifting, that is, I go back to my previous slide, that's a shift up and down, where your g of x is equal to a constant. So we're basically, if it's a minus 2, we're taking our x squared and then we're making it go down 2 by adding -2 to it. Now the next one that I'm looking at here is j of x. So j of x is, in parentheses, x minus 2 to the third power. So taking a look at this, looks like we basically have plugged x minus 2 into something since that's in parentheses. So our parent function here would be something cubed, so that would be f of x equals x cubed. And then it looks like we plugged in x minus 2 into that, so our g of x would be x minus 2. So this is a combination, a function composition, where we plugged g of x into f of x. And that gives us x minus 2 cubed. So if you plug g into f, that is the function composition, that is a shift left or right. So when you're plugging something in, you're changing the x, we're shifting things left or right. So by plugging in x minus 2, this is a shift to the right, because when we have x values, it's the opposite. So if it's a minus 2 when it's involved with the x, we're actually going to the right by adding 2. So that is a shift right. Now the last one here is k of x, which is 1/2 times the square root of x. So our parent function here would be the square root of x, because that is the basic function that we have here. And that we're multiplying it by 1/2. So this is a function multiplication, which means g of x is equal to 1/2. So the combination we're doing is g times f, basically. We're multiplying our function f by what g is. So that's 1/2 times the square root of x. And so that is a stretch or a shrink. When we're multiplying by something between 0 and 1, it is a shrink, basically. We're shrinking all the numbers by 1/2. We're making them smaller. Oops, I'm trying to fix my f. So function transformations are all about what did I plug in and how does that change my function. We're essentially doing combinations and compositions. And the key thing when you're checking function transformations is just to recognize what the parent function is. By either recognizing, okay, did I add or subtract to my parent function, or did I actually plug something in to the parent function? And then from there, determining what the transformation is. So you're not going to have to do things like this in example 5 other than identify the parent function and then the transformation. This was just an example to show you how you're actually doing combinations when you're doing transformations. Are there any questions? All right, clear as mud. Well, is there any? I would just worry about the identifying of the parent function there. That's the okay. Yeah, that's the important thing, is recognizing the parent function. So if I try to highlight here, so like h of x, we have an x squared. So that's the parent function. So that's really the skill that you need to be able to recognize and say, okay, my original function was x, I subtracted 2 from it. For j of x, you want to recognize that you've got, like, okay, something cubed, and then I plugged something into that, and that was a left or right shift. And then k of x, You're so okay. My basic function was the square root of x, then I multiplied that one by 1/2. So it's all about understanding what the parent functions are and then looking to see what you did to them to see the transformation. Are there any other questions? If there aren't any questions, let me look at my calendar. What is the next session? I believe it's tomorrow at 6, I think. Yes. The midterm is not covering functions. Don't worry. Because we knew that you're not going to have these things memorized or understood by then. So no, the midterm is not covering functions. All of this will be quizzed on next week. Yeah, the midterm is just weeks 1, 2, and 3. Let's see. Yeah, so tomorrow night at 6 p.m. I'm going to be doing inverse functions. So that is section 2.7. And that will be helpful for the very last question on the assignment. And then after that, the next one will be Wednesday at 7 when I go over the introduction of the week and everything you need to know. So if you have any questions, feel free to chat me, email me, give me a call. And I hope you have a great Sunday. Enjoy the last day of the weekend before we all go back to work again tomorrow. So I hope you have a great day and that you've had a good weekend.